For this class, we are going to discuss on balancing of reciprocating masses. In the last class, we have seen the balancing of rotating masses, both static balancing and dynamic balancing. In the case of reciprocating mass, the balancing is an introduction to the balancing of engines. So, for that purpose, we can consider a slider crane mechanism. The main components of the slider crane mechanism are a slider, the connecting rod of length L, and a crank of radius R. The acceleration of the reciprocating mass of slider crane mechanism that we derived already in our classes in a dynamic force analysis portion. There we consider a slider crane mechanism, then we derived the relation for the displacement of the slider, then the displacement, from the displacement we derived the velocity, and from the velocity we derived the acceleration of the reciprocating mass. And the acceleration F is given by r omega square multiplied by cos theta plus cos 2 theta divided by n. The force required to accelerate the mass m is given by force is equal to the mass into acceleration. So here the mass into acceleration F. The capital F is equal to small m into small f. So F can be written as m r omega square multiplied by cos theta plus cos 2 theta divided by n. When we are opening the bracket, the force will become m r omega square cos theta plus m r omega square cos 2 theta divided by m. So we can name the first. So F is now the sum of two components. One is m r omega square cos theta, another is m r omega square cos theta 2 theta divided by n. We can name the first component as the primary force and second component as the secondary force. Obviously, the maximum value of a primary force is m r omega square and secondary force is m r omega square divided by n. Now we can compare the magnitude of primary forces and secondary forces. So when we are considering the primary force m r omega square and the secondary force m r omega square divided by n, since the value of n is equal to L divided by R. L is a connecting rod length and R is a crank radius, that is always greater than 1. So the value of secondary force is very less as compared to the value of primary forces. So the secondary forces are not considered in the case of small speed or slow speed engines. But in the case of multi-cylinder engines with a higher speed, we have to consider the secondary forces also. For this case of small engines, we are not considering the secondary forces. Now consider the different inertia forces acting on the slider crane mechanism due to the primary accelerating forces. The primary accelerating force is m r omega square cos theta. So the primary accelerating force is acting on the slider and is given by m r omega square cos theta. So the different inertia force acting on the slider can be considered as considered here. So one is the m r omega square cos theta, and the inertia force is m r omega square cos theta, that is acting opposite to the direction of the applied primary accelerating force. And the another inertia force is the force that is acting in the direction of F34. F34 is opposite to the action of F43, and another one, the third inertial force is F14, that is a inertial force that is exerted by 1 on 4. So there are three inertial forces are there. If the system of forces is balanced, when we are drawing the force polygon, it is closed. So a closed polygon of force polygon is given here with three forces. One is mr omega square cos theta, F34 and F14. These three are the inertial forces acting due to the primary accelerating force. Actually, the primary accelerating force is acting on the slider, so we are considering the forces acting on the slider only here. The another forces are acting are the forces on this frame, that is nothing but the inertial force acting on this fixed member 1, as well as the inertial force acting on the hinge here. So if you are considering the hinge here, the force is exerted by this crank. The force is exerted on this portion when the crank is rotating. So what are the forces acting? The forces exerted by the crank is F21. So the F21, so the inertial force is the force acting on here is F21. So F21, the magnitude or the direction of F21 is always changing because the crank is rotating. Theta, when the theta is changing, the F21 is changing. At any instant when we are considering the F21, we can consider the force F21 is acting on the this portion or this hinged portion of or member 1. So the F21 is always having, at any instant, F21 is having two components. One is a vertical component, F21 vertical, and another is a horizontal component, F21 horizontal. And another force that is acting on the member 1 is F41, that is acting vertically upwards. So in this case, the forces acting on the slider, all the forces are in a complete balance stage, because mr omega square cos theta is equal magnitude and direction to mr omega cos theta, and F43 and F14 etc. F34 and F14 all are complete balance stages, so the force polygon is closed. But in this case is different. Here the force polygon is not closed, so the force will produce this force will produce some type of unbalances or some type of vibration in the slider crank mechanism. We can see how or what are the bad effects of these forces acted on this frame. So two forces are there, like the forces F21 and F41, and F21 is having the vertical component and horizontal component. So when we are looking to here, we know that the vertical components F21 V and F41, so these are perpendicular, or these are two forces that is acting in opposite two direction and separated by some distance. So in for a complete balanced stage, this force these two forces may be of a equal magnitude, that may be balanced. So the vertical forces may be balanced in this case, but the vertical forces F21 vertical and F41 may produce some couple. But so this case of the vertical forces is balanced, but when we are considering this horizontal force, the horizontal force again remains as unbalanced force. So what is the effect of this vertical force producing couples and the unbalanced horizontal force? We can discuss in the next slide. So the force exerted by the crankshaft in the main bearing has two components that we already seen. The two components are F21 vertical and F21 horizontal. The horizontal component is unbalanced, is called the unbalanced shaking force. And the vertical components, the unbalanced vertical forces F21 vertical and F41 vertical balance each other, but it produces an unbalanced shaking force that we discussed in the last slide. So here two unbalances are there. One is a unbalanced shaking force and another is a unbalanced shaking effect. What is its effect? The shaking force produces linear vibration. So the effect of a shaking force is that it will produces linear vibrations, and in these directions, linear vibrations, but the horizontal in the horizontal directions, whereas the shaking couples produce oscillating vibrations. So oscillating vibrations is nothing but it will produce a up and down movement, so it is a more vigorous in this case up and down movement. So the magnitude and direction of these forces and shaking couple will goes on changing with the value of theta because the crank is rotating. So the next step is how to balance this unbalanced shaking force. So shaking force is the only unbalanced force that may hamper the smooth running of the engine, but the effect of the shaking force is more vigorous than the effect of the shaking couple, because the shaking force may produce more vibrations. So actually, if a force is unbalanced, what is a normal approach? When the normal approach is that we will introduce a counter mass of magnitude m at a radial distance r. Here the radial distance is the crank radius, directly opposite to the crank. But when we are adding this force m, or this mass m, what is the effect? We can see what is the effect. The effect is nothing but when we are adding the mass m at a radial distance of r diametrically opposite to the crank, it rotates along with the crank. So when the crank is rotating, it will always changes its position from one point to another point around the circle. And the main effect is that the mass produces the force, and that force is nothing but the centrifugal force. So when this centrifugal force is having two components, so when it is rotating at any instant, the centrifugal force produces two components. One is mr omega square sine theta is a vertical component, and mr omega square cos theta is a horizontal component. So mr omega square cos theta is nothing but our applied magnitude is the same as our applied inertia force or applied accelerating force. So but this is not same as the magnitude of applied force. So this primary force, when it is acting, this will opposite to the primary force that will balance the system. So but this mr omega square sine theta, that is a vertical component, always acts as a unbalanced systems. So how to balance this thing? So it is not possible to complete balance, even though it is this horizontal component can be balanced completely, but the vertical component cannot be balanced completely. So we are making some compromise in balancing in this type of systems. We are not completely balancing the system, we are going for something like a partial balancing. So we are not completely balancing in this case of slider crank mechanism, we are partially balancing only. So the centrifugal force, we discussed it has a horizontal component and a vertical component. The horizontal component is in line of action or in the line of stroke, acting to the direction of applied force, and it neutralizes the unbalanced reciprocating forces. This is a primary applied force, not a applied inertia force. It neutralizes unbalanced reciprocating forces. But this perpendicular component mr omega square sine theta is perpendicular to the line of stroke, always remains unbalanced, as we discussed in the last slide. And what is the effect? The effect is nothing but instead of sliding to and fro, it it causes the mechanism to move up and down. That is the effect of this mr omega square sine theta. And the magnitude always changing like sinusoidally, like this is mr omega square sine theta. So the magnitude is very high or maximum at the middle portion. It is that is angle is 90 degree, or the angle is this 90 degree, or angle is 270 degree. And when the angle is 0 degree, or when the angle is 0 degree or 180 degree, the magnitude is 0. So like a sinusoidal wave, it moves up and down, and it will produce a jumping effect on this slide climb mechanism. So to minimize the effect of unbalance, the only thing we can do is we have to make a compromise. So we are taking not a complete balance, we are considering we can take a partial balancing. In the case of partial balancing, in this case we are taking 2 by 3rd of the reciprocating force is balanced. So normally the value of C is a fraction of reciprocating mass balanced. So the fraction always between half and 3 by 4th normally. So in between we are taking 2 by 3 for our purpose. And the primary force balanced by the mass is C mr omega square cos theta. This is a primary force. Primary force is a applied force on the slider, and the primary unbalanced force is the remaining force, that is a 1 minus c into c mr omega square cos theta. And the vertical component of so here there is no c is there, 1 minus c mr omega square, I think so. And the vertical component of the centrifugal force which remains unbalanced is cmr omega square sin theta. So the resultant unbalanced force can be written for at any instant. It can be written as root of 1 minus cmr omega square cos theta square plus c into mr omega square sin theta square. So this value, the resultant unbalanced, is minimum when the c is equal to 1 by 2, when it is a maximum when it is a 3 by 4, and the resultant balanced force is minimum when it is a c is equal to 1 by 2. So thank you.